share the entire screen. Okay, I need to start the recording, right? Okay, the recording is started. Okay. Okay. So yeah, I hope the screen is visible. Right. Guys, yes, no?
Yes, ma'am, it's visible.
It's visible. Okay. So so we were looking at LP duality, and I told you about this method of including multipliers. Okay, you take an optimization problem, a linear program, and you multiply each of the constraints. So the idea is when you have a minimization problem, you try to get a lower bound for the problem. Okay, and what's the best lower bound that you can get? So that's the idea of the dual. And if it's a maximization problem, what is an upper bound for this problem, and what is the best upper bound that you can get? Okay, so that's how the dual is written, and we sort of went through these concept of including these multipliers. Okay, so one thing I want to mention is that the LP needn't be in this form, like A transpose X greater than B. I mean, you can have things like AX equal to B or AX less than B. That's also fine. But if it is in this form, like you have a method to write the dual, and for all other forms, you can convert it into this form. So I don't mean like using surplus variables or free variables. It's not in that sense. But so the concept of slack, surplus, and free variables, that was primarily needed for the simplex method. Okay, but now any inequality that you have like this, you can flip it. I mean, you multiply the whole thing with and it gets flipped. So in this manner, you can convert other LP forms into this kind of a form as well. Okay, so that will be useful when you write the dual for the other forms. Okay, so what we went through was that you multiply each of these constraints. So corresponding to each constraint, you have a variable, a y, and then the thing was you wanted to. So what you then you just sum up all the constraints. So what you get is B transpose Y on the right hand side. So it's basically B1 Y1 plus so on up to B and Yn, and that is exactly B transpose Y. And because the x's are greater than 0, so these multipliers, you don't put them for these greater than or equal to constraints. For these, you don't include because that is getting incorporated in a different manner. So the way in which it's getting incorporated is this, the sign gets maintained, the inequalities get maintained. So B transpose Y becomes less than, y. So there's actually Y transpose AX. So if you just multiply each of the constraints with these multipliers and sum them up, what you'll get is B transpose Y is less than Y transpose AX. So this part. Now you additionally wanted to enforce that this Y transpose AX is less than C transpose X. So by less than, it's like component wise. So each of this is a vector. So each of these is a vector. So Y1, A1, you have this component, and you have Yn, so on up to Ym transpose AM. Okay, so that you want it to be like term wise, you want it to be less than Ci. Okay, C1 should be greater than Y1, A1 transpose, and so on. Okay, so that was how we wrote the dual. So you want this is a lower bound, this B transpose Y, you want it to be a lower bound, and you want it to be a strong lower bound, as good as possible. So that's why you try to maximize this lower bound. And you want indeed C transpose X to be greater than B transpose Y. So a way to achieve that is by adding these constraints. A transpose Y less than or equal to C, and you also want Y's to be greater than 0. Okay, because if Y's are not greater than 0, then this side of the inequality can get flipped. Okay, so that's the reason why you put that. Now, similarly, like for other forms, we saw that if you didn't have X as to take values greater than 0, there'll be some modifications to the dual. Okay, so in particular, you have this inequalities, the set of inequalities you want it to be maintained. Now, for this part, you want Y to be greater than 0. But here, since X is given as unrestricted, you cannot guarantee this. Okay, so that's why you ensure that A transpose Y is equal to C. Okay, so now in this context, I also want to tell you that, like for other forms, you could have something like this, right? So now so another example may be like minimize C transpose X such that AX equals B. and x greater than 0. Okay, so in fact, this is one example that we were coming to. So if you have an example like this, one way is, you can directly use this principle. You multiply each of these constraints with a multiplier and then see whether y should be greater than 0, or whether you have these inequalities to be maintained and things. Another way is that you can also write it. This is equivalent to minimize C transpose X such that AX is greater than or equal to B, and also AX less than or equal to B, right? So it's the same. You can just replace this with inequalities. Okay, so now this AX less than or equal to B, that is just, it is the same as minus AX greater than or equal to minus B. Okay, so now you can write the same way that we did. I mean, you can stick to one form and then you can also derive the dual based on that. So this is in the form that we saw earlier, right? So it is of this form, minimize C transpose X subject to AX greater than or equal to B. Okay, so then you will have a set of multipliers here. So this will be, let me call this y. Okay, and this will be z. Okay, so this is a vector. So this is a set of m constraints. So m constraints in n variables. And again, this is also the same set of m constraints. I mean, it's just with the signs flipped. Okay, so these are m constraints again. So y's, there are m of them, and the vector z also, as far as that is concerned, there are m of them. Okay, so now when you do the same principle, what you get on the right hand side is b transpose y minus z, right? I mean, I'm just multiplying these constraints with y and this with z and summing them up. So the right hand side becomes b transpose of y minus z. Okay, and now this will be less than ay. So y, so let me just write it. So yeah, so it will be y, so it is y transpose ax minus, okay, let me just write it again. So y transpose ax and minus z transpose ax. Right, so multiplying each of these constraints with y is going to give you this kind of an expression, this with y and this with z, and this is greater than, you can just write it in the same way. Like if this is confusing, you can just change the order. So this is just going to give you a number, so that's why I didn't pay too much attention to the order. So y transpose b minus z transpose b. Okay, and you want this in turn to be less than C transpose X, right? And so because you care, I mean, these are all inequalities, so you want Y and Z to take values greater than or equal to 0. Okay, so now the LP form that, by the previous logic, what we had was we would say maximize this form, this part, right? This is the lower bound and you want it to be maximized. So let's just say it's B transpose Y minus Z, okay? And subject to this part, right? So the coefficients of X should be less than or equal to C, term by term. So component by component, you want these coefficients to take a value less than C. So that would be A transpose Y minus Z less than or equal to C. Okay, and you have y greater than 0 and z greater than or equal to 0. Okay, so now when you do this, you can relate this to something you've seen earlier. So y and z are greater than or equal to 0. So this is equivalent to writing, you can replace this y minus z with some variable w. Okay, and with w is unrestricted. So this would become max b transpose w subject to A transpose W less than or equal to C. And now W is unrestricted. Okay, so this is also another way to, write the dual. Like you understand it with respect to one of the forms, so particularly this form, and then extrapolate it to other forms that come. Okay, so this is exactly the dual. I mean, if you try to, I mean, I think we started writing this for the transportation example. So this is also another way in which you could derive the dual for other forms. Okay. So are there any questions on this? Can I hear your thoughts on whether this idea is clear or not? Yes. Yes. Okay. What about the others? So that's clear. Okay. Lakshmi?
Ma'am, would you please explain the transportation problem one more time?
Yeah, I will come to the transportation example. I will apply this to the transportation problem, but I want to get a sense of whether this method of writing the dual is clear, like this general principle. That's clear? Okay. Okay, so good. I see a lot of responses saying it's clear. So these are the ways in which you come up with the dual. And then we saw this diet problem. Okay, and then we saw an interpretation for the diet problem, and we were doing this transportation example, and that's where we stopped in the previous class. Okay, so now so this transportation example, if you recall, it's where you want to send, you there's a company, okay, maybe something like MTR, or some manufacturing company, or whatever, and they have different origins. These are the factories, and there are these destinations in which there's a demand for these products. Okay, and you want to send products. Okay, so the maximum amount that can be sent from each of these origins. So there are a few origins here, and the number of, you can, from this, the first origin, you can send at max A1 units of a product. Okay, and at the destination, there's a demand of B1. Okay, so the total amount that you send from this origin, this factory, to all other destinations cannot exceed A1. It should be exactly equal to A1, because you don't have a scope for maybe storing things, and maybe that could be the constraint. Okay, and at the destination, you don't want to receive. You want to receive exactly B1 unit. Okay, at this destination. So for all the destinations, you want to receive exactly the BJ units. So the incoming, whatever you get on each of these incoming arcs should be exactly BJ. Okay, so that's why this is a constraint, and there is a cost for sending some products, some units from I to J, and the cost for each unit is CIG. So this is what you wanted to minimize. So the MTR is trying to minimize this kind of an objective subject to these constraints. So what is how much should what is the amount of quantity that has to be sent on each of these links? Okay, so now we were going to take the dual here, and so we started off by multiplying this with UI, each of these origin constraints with UI, and each of these destination constraints with VJ. So now I'm just going to apply whatever we just wrote now. Okay, so it's exactly in this form: minimize C transpose X such that AX equals B. Okay, and X greater than 0. So this is exactly of that form, right? So the dual is just in this manner: maximize B transpose W such that A transpose W less than or equal to C. So it's as if my U's and V's are getting substituted for the W. Okay, so let's just write that. Okay, so I see that. I hope the screen is visible and it's not looking cluttered. Please let me know in case it's not visible. Okay, so now the dual, so let me just write it here. So what the dual was supposed to be something like this: maximize B transpose W such that A transpose W is less than or equal to C, and W is unrestricted. Okay, so let's just apply what it means here. So can somebody tell me that? Just apply these values. U's and V's are taking the place of W. So tell me the objective. So it's maximization. So guys, okay, can someone tell me the dual? Like maybe Aditi?
Ma'am, actually I joined in a bit late, so I'm
Okay.
kind of lost here a bit.
Okay. So Yeah. Okay. So take your time. I just wanted to, like, okay, can somebody else maybe attempt this about how to write the dual?
Ma'am, summation AI into UI plus summation BJ into VJ.
BJ, right? AI times UI plus summation BJ times BJ, right? So I is the set of all origins and the summation J is over the destinations. Okay. What about the constraints? Anybody? Maybe Siddharth Shah. Yes. Siddharth, you're there? Okay. Okay, I don't hear any response from Siddharth. Anybody else? Okay, Manan?
Ma'am, can you switch back to the problem?
Yeah.
Okay, so
So what you need to do is you need to take each of the xij's and you need to see what the coefficients would be. Like if you sum up, you multiply this with ui and this with vj, and then you sum up and see what is the coefficient of each xij. So let's fix an ij, okay, an I in origin and j in destination. So now can you tell me what are the coefficients that would come up?
Xij ui plus Xij vj less than equal to that Cij.
Less than or equal to Cij. So that's what's going to come, like Xij times Ui. So it would come like in this form, Xij times Ui plus Xij times Vj. You want this to be less than Cij, Xij. I mean, translating what we saw earlier. So then the coefficients of Xij are exactly Ui and Vj. And you want this sum, Ui plus Vj, to be less than or equal to Cij, right? So the dual will not have any of the x's, okay, because it's only the coefficients. So it would be ui plus vj. So whatever xij is there, the coefficients of that. So ui plus vj should be less than or equal to cij for all ij, for all I in the origin and for all j belonging to the destinations. Okay, and u and v are unrestricted. So this is going to be the dual. Okay, so I don't know if people are clear. See, if something is unclear, you have to ask, because if this part is not clear, then general constraints won't be clear. Yes, Siddharth.
Ma'am, I'm a bit lost in the notation. I forgot about the transportation problem. That's
Okay.
why.
Okay. So, okay. So, do you want me to go over the transportation problem again?
Yes, ma'am, just the notations. Like I understand the problem, but I cannot recall the notation.
Okay, so the thing is, so AIs are giving you the amount of, how much you can produce at each of these origins. Okay, at each of these sources you can think of, and BJ's is the demand at the destination side. Okay, so you have to send Xij quantity from all the A's, the origins to the destinations. Okay, and so that you have to decide how you want to achieve this. Like you want to send some quantity, you want to send it in such a way that the destinations have these b's, you get exactly bj quantity at each of the destinations. Okay, so this d is the set of the destinations and o is the set of the origins or the source. Okay, and xij is your decision variable. You want to see how much you want to send, okay, in each of these links from each pair, from each origin to each destination location. Okay, and the cost is cij. The cost of sending each unit of product from I to j is cij. Okay, so the objective is just minimizing this double summation. And in terms of the constraints, what you're going to have is how much you send out from this location. Say the first location, the source, the amount that you send out is the sum of all these, right? You take every destination and then you sum up these xij's, right? So from fixed origin, so suppose the first origin you take, so origin 1, Okay, and the total sum x11, x12, x13. Okay, so all these things you sum up, and that is the total quantity that you're sending out from source 1, and that should be exactly equal to A1. Okay. Similarly, for the destination, whatever comes in. So here you're fixing the J, okay, and whatever comes in. So the first destination, things that come in are, from the first source, from the second source, and so on. So that's where you have the summation xij for I in the origins. So fix a J, and take the sum over all the origin locations, and that sum of the xij should be equal to bj. Okay, and of course you want xij's to be greater than or equal to 0. Okay, so Siddharth, is it
Yes,
fine now?
clear now. And ma'am, what was UI?
Yeah, so now, right, so here we are taking the dual. Okay, so now with this is the primal problem. This is called the primal. Okay, and we are writing the dual of this problem. So for doing that, we are using these multipliers. Okay, the same concept that we saw last time. You multiply each of these constraints. So for each of the sources, you multiply these with some UIs. Okay, and the destinations, you multiply it with some VJs. So the number of U's, so U is going to be a vector, and it's as big as the number of origin locations. And the number of V is also a vector. It's as much as big as the number of destination locations. Okay, so this is going to be, your dual is going to be an optimization problems in term, it's going to be an optimization problem over U and the V. Okay, so so then you just apply whatever we did in the last time and what I just told you in the beginning of this class. So where you, it's a maximization problem, and you get it by, okay, so I think this B, and I hope this B and this B doesn't confuse. So here, this is from the general form. Okay, so if you have the original optimization problem is, min C transpose X such that AX less than or equal to B, right? So so AX greater than or equal to B, and so and those are, I mean, in this notation, that's what I refer to. Okay, so here this B means it's the right hand side. It's this collection of A and B. Okay, it's a vector of all the origin components, the AIs, and for the destinations, it's all the BJs. Okay, so that vector is this B. Okay, the right hand side of the constraints. So when you substitute that, that's just going to be, and these are the variables. So this takes the form of U and V's. So so B transpose W, it's just, in terms of the transportation problem, it's just summation AI UI plus summation BJ Vj. Okay, and now this A here, this is a constraint matrix, so it corresponds to whatever is on the left hand side of this constraint. Okay, so so if you try to write it exactly like construct this matrix A, it gets a little bit cumbersome. So instead of that, what you do is you just take xij. Okay, so each of the variables, and you take its coefficients. So if you do this multiplication and you sum it up, then what you're going to get is, in terms of the xij, the coefficients would be for each of the origins. So for origin I, you're going to have this ui component. And for the destination j, this constraint is going to give you a vj. This xij is going to come up here, and it will come up with the multiplier vj. Okay, so the coefficient is just ui plus vj. Okay, and that should be less than cij xij. Okay, so is it clear now?
Yes, ma'am. It's clear.
It's clear? Okay. Okay, so this is a dual of the transportation problem. Now, if you look at this, there's some other interpretations. The original transportation problem was from the view of a company like MTR or anything, which was sending, items from one of its factories to another destination. Okay. Now, this, in terms of the dual, you can think of it as an alternate problem where there's an entrepreneur. Okay, so maybe like some of you guys, like maybe Manan, okay, after your undergrad, you go up, you're going to start a company, and you realize that you have enough resources to carry out shipping of items. So what you'll do is you'll come up to this company and you'll say, okay, you don't have to worry about this cost of transporting. I mean, you don't have to worry about transporting items. I will take care of that for you. But what I'm going to do, what you would do is at each of the sources, the company has to pay you UI. Okay, UI is the amount you charge at the source for picking the product, and VJ is the amount that you charge at the destination for delivering the product. Okay, so the revenue, your revenue as an entrepreneur, Manan is going to get this as the revenue. Summation AI UI plus BJ VJ, because this is the amount that is going to be sent from the sources, and this is the amount. BJ VJ is what is received at the destination. Okay, and this constraint, it means that the total amount that you take each shipment, whatever is being transported from I to J. Okay, now if UI plus BJ, so this is the total amount collected from that movement of that good from I to J. Now this sum has to be less than the cost. Okay, if MTR had to just take they themselves had to transport the item, the cost they would incur was CIG. Okay, but if this UI plus VJ, I mean, this is the new cost that they will pay. So suppose they didn't take care of the transportation themselves, but they gave it to Manan. This is the charge they will incur, UI plus VJ. So they will take Manan's services only if this UI plus VJ is less than their cost, CIG. If it is greater, then they will say, okay, we can do it ourselves. Why should we ask somebody else? Why should we go through a third party? Okay, so okay, so this is how the interpretation of these constraints. Okay, and so this is the dual is the assignment of prices, how much price you assign to how much you collect from the source and destination, and so that your revenue is maximized. For the entrepreneur like Manan, the revenue has to be maximized. Okay, but still at the same time ensure that the services are used. Okay, so that is the interpretation of the dual for the transportation problem. So is this notion clear? Manan, if you're going to do this seriously, yeah, this might come of help. So is this clear?
Yes, ma'am. The explanation was clear.
Okay, fine. So in this manner, like if you write for many problems, the dual has some good interpretation. So let's just go to the next one. I mean, I want you guys to try this out. So this is the original network flow problem. So in the first class, we looked at this max flow problem, and many of you gave solutions on how you will send flow from a source to a destination. It was this oil delivery example where there were some capacity constraints on each of these links. Okay, and you gave some examples on how you can construct a flow. And we also saw that you can formulate this as a linear program. Okay, so this here, the linear program was in terms of the variables x and v. Both of these are variables. Okay, and v is unrestricted. Okay, so so try to see what the dual gives you here. Okay, you can do this by the same logic that we have been seeing so far. Okay, so just try this out as a homework. At some later point, we'll probably come back to this. I hope there is time, but yeah, this should be a good exercise for you. Okay, so now if you remember, the way we constructed the dual was to always find a lower bound for a minimization problem, or if it was a maximization problem, it was an upper bound. Okay, so let's just say this original LP in the minimization form, the min C transpose x such that ax greater than or equal to b. Let me say its optimum value is p star. Okay, and the dual is this: maximize b transpose y such that a transpose y less than or equal to c and y greater than or equal to 0. And let me call the optimum of this problem b star. Okay, so by the way we constructed all these constructed the dual, it's true that d star is always going to be less than or equal to p star. Okay, so the dual objective is always going to be less than the primal optimum. the dual optimum is always going to be less than the primal optimum. Okay, so it's quite intuitive because of the way we construct it, and if you can also see it from these constraints if you want to do it algebraically. So you have this, right, b, so b is less than or equal to ax. So if you take b transpose y, okay, so if you take any dual feasible point y, so by dual feasible I mean something which satisfies this, a y such that these set of inequalities are satisfied, and primal feasible is any x such that this is satisfied. Okay, so may not necessarily be the optimum. So let's just take any feasible point, okay, any feasible primal and dual solution. So if you take b transpose y, so because in the primal you say that is less than or equal to ax, so this is going to be less than x transpose a transpose y. Okay, and now because y is dual feasible, a transpose y, its component wise it's less than or equal to c. So each component of this is less than c. So overall, and x's are all positive, I mean non-negative quantities. So overall this is going to be less than x transpose c. Okay. So you can expand this out and see it more clearly. So this will be xi times a transpose y and the ith part of that, the ith component of that, and a transpose y, the ith component is less than ci, less than or equal to ci, and xi is greater than or equal to 0. So that's why this is overall going to be less than or equal to x transpose c, which is same as c transpose x. Okay, so this is actually called weak duality theorem, which says that if you take any primal feasible point and any dual feasible point, this relation holds true. Okay, so now in particular, it's also true for the optimum, right? So this is true for all primal feasible and dual feasible values. So in particular, if you take the optimum value of the dual, you're going to get the maximum value of b transpose y, and that is just d star. And here, if you take the minimum value, you're going to get c transpose x star, which is just p star. So this is always going to be true. Okay, so this is called the weak duality theorem. Okay, so now another thing to note is also that if you, these duals are symmetric in the sense that if you take this dual problem, this one, that's maximization problem, and if you try to write its dual, you will get back this original primal problem. Okay, so you should try to see that, I mean, maybe try it out later. So that will also give you some practice with this. Okay, so in general, for writing the dual, one reference is this Lieberman book. Okay, so they have everything written it out as constraint in the primal form. It corresponds to a constraint of the dual. I mean, it corresponds to a variable in the dual. So if the constraint is of less than or equal to form, then the variables in the dual side is greater than 0, and so on. So these are a set of rules. You can derive all of this using the technique we did in class. So you should go back and just ensure that you're able to verify that these what you get is exactly in accordance with this table. Okay, you can use this as a reference also for writing the dual and just checking things out. Okay, anyway, so coming to weak duality, this is the thing that it's a simple statement based on how we constructed the dual. And now, based on this, one thing that you can see, okay, so there are various possibilities, right? So here, what the weak duality theorem just said was that the primal is this is the minimum value, so let's just say this is p star. Now d star, all the dual feasible values will take an objective somewhere here. So what I'm writing on this line, on this number line, is just the objective values taken by any primal or feasible solutions. Okay, so if p star, this is the minimum value, so this is the set of all objective values that the primal can take. Okay, primal feasible points will take an objective here, and this is the set of all possible values that the dual feasible solutions will take. Okay, so d star will be somewhere here. It can be here, it can be here. Okay, but it cannot cross over here into this space. Okay, so now based on this, you can, there are different things. So the primal can, it can have a finite optimum. So by that, what we mean is that it is feasible and there is an optimum which is not, negative infinity. Okay, and another possibility is the primal can be feasible, but it's unbounded. Okay, so there's a feasible point, but the optimum is like minus infinity. And the other case is when the primal is not even feasible, so that's infeasible. So what happens to the dual? Which of these can happen? Okay, so let's just try to analyze this. So if the primal has a finite optimum, so something like this, okay, so can the dual have a finite optimum? What do you think? Yes, no? Okay, am I speaking to myself? Guys, I need some response. I cannot proceed without a response. Yes, it can have. Maybe says yes. Yes. So this can be finite, right? So this is possible. Now, can the dual be unbounded? So when the dual is unbounded, what we mean is that the dual is a maximization problem. So if we are saying the dual is unbounded, it means the objective is somewhere here. I mean, it's like positive infinity. So the primal takes this value p star, the optimum is p star, but the dual is positive infinity. Can that happen? No.
No, ma'am.
No. Okay, good. So this is not possible. Now, can it be infeasible? Can the dual be infeasible? So again, in this case, primal is optimum. Yes.
And will be on negative infinite side in unbounded.
No. So if dual is negative infinity, it means that there is no feasible point, right, for the dual. That's what it would mean, because you're trying to maximize an objective.
Okay.
Okay, so when you say unbounded for a maximization problem, it means it goes to infinity. So yeah, so can this be that it's infeasible? Can the dual be infeasible? Yes, no? Answers? What do you think? Or unsure? What do you think? No idea. Unsure. Okay. So unsure. So technically, it seems like it can happen, right? I mean, the primal is getting a grounded value at p star, but the dual, there is nothing that is feasible. Okay, so it seems that, I mean, just looking at this notion, this weak duality theorem, it seems like it's possible, but actually, it turns out that it's not. This also cannot happen. So the proof of this, you can try. I mean, it will make use of Farquhar's lemma. So I'm not going into this proof here because I think it will just divert the focus of what I want to get into. So you can prove this using Farquhar's lemma. Okay. So it turns out it's not possible. So these two, to get this, we used this weak duality notion, right? So by weak duality, this unbounded cannot happen. Okay, so now, and even this one also by weak duality. Okay, so now by if the other case where the primal is unbounded, so that means this is the case where the primal takes a value of minus infinity. Okay, so that's the primal. So now, can the dual have a finite optimum? Yes, no? No. So the dual cannot have a finite optimum, because if it had, then it would violate this weak duality theorem. So that's not possible. Now, can the dual be unbounded? So by dual unbounded, it means the dual takes a value somewhere here. It's like, again, plus infinity. It's feasible, but it's unbounded. So can that happen? No. No. Good. So this is not possible. Now, can it happen that the dual is infeasible? So yes, the dual can be infeasible here, right? I mean, you cannot find any point which satisfies the dual. So it's as if the lower bound is also negative infinity, and anyway, the primal is negative infinity, right? So this can happen. Okay, and in fact, this is the only thing that will happen for this case of unbounded. Okay, now let's look at this other case. Now, when the primal is infeasible, So primal, so you cannot have any feasible point here. So can the dual have a finite optimum? Can it be unbounded? Can it be infeasible? So which of these do you think is possible? Infeasible, right? Unbounded and infeasible. Unbounded, yeah. So correct. So all your answers are correct. So these two cases can arise, but finite optimum, this cannot happen. Okay. So you can also think of it in terms of, if you take the dual as the primal. So if it has a finite optimum, then its dual is infeasible. So that also cannot happen. Okay. So these are some of the possibilities that you can arrive at using this weak duality theorem. Okay, so I would urge you to try to prove this. When the primal has a finite optimum, the dual being infeasible, this cannot happen. So I would strongly urge you to try this on your own. Okay, so now like we saw. Yes.
In case of unbounded, when we were like, why can't it be unbounded to the dual?
Which case are you telling?
When the primal is unbounded,
This case, yes.
and dual is like, we said that dual cannot be unbounded.
Yeah.
When the primal is a maximization problem and it's going to plus infinity, and we are trying to bound it from like give a lower bound to it. So in that case, can't it also be unbounded?
So this is the case when the primal is a minimum and the dual is a maximum. Okay, so now if the primal was a maximization problem, the dual is going to give you an upper bound, right? So so if the original primal, you start off with a maximization problem, then all these things are going to flip. Okay, so let me just write it here. So if primal is of the form is a maximization problem, then what you're going to have is that primal optimum is this, and the dual optimum is an upper bound. So this is going to be less than or equal to D star. Okay, so weak duality is going to boil down to this in that case. Okay, so now if the primal is unbounded, so it's a maximization problem, and so the maximum value is plus infinity. So P star is like positive infinity, and so if D star is unbounded, if the dual is unbounded, it means that D star is going to be negative infinity because it's a minimization problem. So that cannot happen, right? Because it was an upper bound. The dual was always an upper bound. Okay.
Yes, ma'am.
That's a good point. Yeah, that's a good point, Siddharth. So actually, in the way that we are defining the dual, we are taking the primal as a minimization problem and the dual as a max. So all these things will flip if these inequalities will flip if you start off with a primal as a maximization problem. Okay. So again, try to see for a maximization problem, you go back and try to see if this table makes sense or not. Okay. Yeah. So that's.
Ma'am, I have a doubt in the case when primal is infeasible. So, ma'am,
Yes.
how can the dual be unbounded? Because unbounded would mean that we can have as good as we want it to be.
Okay. So let me. Yeah. So let me say. So that means. So if the primal, let me say it's a minimization problem. Okay, and there is no point that is feasible. Okay, and now in terms of the dual, so like there is no bound here, like the primal, there's no P star here. Okay, so now in terms of the dual, if you take, so when it's unbounded, it means that the dual is somewhere here. It's like plus infinity. Okay, so what did we want? This is technically possible because there is nothing which is primal feasible. Right, so there is there's nothing which binds the dual in any manner. Okay, so that's the reason why we say that the dual can still become unbounded.
Ma'am, but what does it intuitively imply?
So it's okay. So in that sense, it's going to be a very meaningless problem. Like there is no feasible primal, and the dual also it's like it's an it's like plus infinity. So in terms of the intuitions, yeah, there is really not going to have. I mean, if you look at those kind of problems, you're not going to get anything from it. But in technical, I mean, in terms of the technicality, it is possible. Right. I mean, if you look at this relationship, it is definitely possible to have this scenario. Right. Yeah, you might not get anything meaningful out. I mean, there's no meaningful bound, right? Like if you look at this as an infinity and an infeasible, if a minimization problem is infeasible, it's usually represented as the optimum is like plus infinity. So minimization problem, if it's feasible and unbounded, it means that the optimum is negative infinity. But if it's infeasible, it's as though you're saying like it's plus infinity itself. Okay,
But
so
ma'am,
there's no possibility. Yeah.
if we think about it this way, that the primal, so there was no solution to the primal. But and if we try to find not the optimal but some solution, then the primal doesn't give any solution, but the dual gives some solution. Not the best. I mean, we don't want the best one because the best one is unbounded, but we can get some solution. So what does that solution intuitively mean?
Yeah, so you can get some solution. So if the moment it's becoming unbounded, so that means there is some solution. What we mean is it's feasible, but it's unbounded. So that it's giving you some value. So it's not a very meaningful statement here in terms of the connection with the primal. Yeah. So in terms of the value, you will get something. You could get some. I mean, there is some feasible point in the dual, but it's not telling you anything in terms of the connections with the primal, right? So,
Okay.
right. So yeah, this case, I mean, these are like some corner cases sometimes you will have, but it does not buy you anything in terms of, what kind of problems you solve and things. Okay. Yeah. So just try to, get a better sense of it, go back, try to internalize this. So what I want to do next is, focus more on this case where the primal has a finite optimum and, the dual also has a finite optimum. Okay. So in that case, how do these values P star and D star compare? So in terms of weak duality, if it was a minimization form, as always, we know that this is true. D star is less than or equal to P star. Okay, but can we say anything about this difference between P star and D star? Okay, so that's going to be the next topic. So that's called the duality gap. So it's the difference between the optimal primal and the dual problems. Okay, so for the particular LPs, the primal we took as a minimization form, this difference, P star minus D star, is what is called the duality gap. And what weak duality theorem is saying is that this duality gap is always going to be greater than or equal to 0. Okay, but what we want to investigate further is, can it be equal to 0? Okay, so now it turns out that for linear programs, okay, so if if in the case where these primal and dual, they have the finite optimum solution, so when in that case, even the other pair, so if the primal has a finite optimum, the dual is also going to have a finite optimum, and in particular it's going to have a duality gap of 0. So the primal and dual pairs will always have an exact equality. And at the optimum, they will have the same value. So P star and D star will be equal. Okay, so that's one thing. That's a good feature about linear programs. So what it's telling you is, if you can solve the dual in some efficient manner, then you already have the optimum value of the primal. Okay, so that the dual is helping you in some sense to solve the primal. Okay, and if either problem is unbounded, the other is infeasible. So this is just the consequence of weak duality theorem. Okay, this we already saw. Okay, so yeah, so so I wanted to go over the proof of this theorem. So this is going to make use of Farka's lemma extensively. Okay, so I don't know, maybe we are running out of time, so it's just 5 minutes left. So maybe, okay, I'll start from here in the next next class. Okay, so yeah, so I think I'll stop here if there are no other questions. And I might want to actually take another class on Saturday. So I will let you know about this, because I mean, if there is a requirement I might take over the machine learning class that you have on Saturday morning, right? You have an extra class. I'll talk to Satya, and we have been discussing about this because he wanted me to go over duality sooner. Okay, so I'll let you know depending on how we proceed in tomorrow's class and all that. Okay, so thanks for being here. If I'll hang back if there are any questions. Otherwise, see you tomorrow afternoon at 2.
Thank you, ma'am.
Thank you, ma'am.